Signals and Systems, Infinite Fourier Series, Series on Signals and Systems, lecture number 2.11. This is second part on Infinite Fourier Series. In the first part, a preliminary treatment, a basic treatment, a fundamental treatment of infinite Fourier series is given. In this second part, continuation of the treatment to the first part is given. Now, let us move further to complete the treatment of infinite Fourier series. Conversion formula. What is this conversion formula? In total, 3 types of expansions. They are introduced in this session: exponential and trigonometric. In trigonometric, 2. These 3 forms, they have certain relationships among themselves. These relations or relationships can be used for benefit. What is the benefit which we can get from these relations? If we know exponential Fourier quotients, Fourier series expansion quotients, from them one can find trigonometric Fourier series expansion quotients. If we know trigonometric Fourier series expansion quotients, from them one can find exponential Fourier series quotient. One need not do both. So from one, other quotients can be obtained. Here in this slide, the relation between various quotients, they are given. A0 is equal to F0. F0 is exponential Fourier series quotient. An is equal to Fn plus f of minus n, f of f minus n. Bn is equal to J Fn minus f minus n. So this first line or first row gives relations which are useful to find trigonometric quotients from exponential quotients. Now second row, it gives us the relations which are useful to find exponential quotients from trigonometric quotients. F0 is equal to A0, Fn is equal to half An minus JBn, F minus n is equal to half An plus JBn. Third row is, it's already mentioned in an earlier slide. This is from compact or harmonic form and sinusoidal form relation. A0 is equal to A0. Capital A0 belongs to compact form, small a0 belongs to sinusoidal form. Capital An is square root of an square plus bn square. Angle phi n is minus tan inverse bn by an. Now let us spend some time on Dirichlets conditions. What are Dirichlets conditions? While starting the session, it has been told that Fourier series, that is infinite Fourier series expansion, is available for periodic signals, periodic continuous time signals. However, there is a condition. Not all continuous time periodic signals can have Fourier series expansion. Only some. Only those which satisfy conditions, certain conditions. These conditions are called Dirichlets conditions. Hence, one can say that only CT periodic signals, which satisfy Dirichlets conditions, they only can have infinite Fourier series expansion technique available. Others, they don't have this expansion. Now let us see what are Dirichlets conditions. The two conditions, bounded variations and absolute integrability, these are called Dirichlets conditions. Now let us move further. For the existence of Fourier series, the periodic function f of t must be absolutely integrable over an interval of one time period. Absolute integrability means f of t must be such that integration over one time period, absolute f of t dt should be less than infinity. Means it must be finite. This is called weak condition. Another condition is there, strong condition. This strong condition refers to bounded variations part of Dirichlets condition. What is this bounded variations part of Dirichlets conditions? For the uniform convergence, the function must be finite and can have only finite number of maxima and minima and finite number of finite discontinuities in a time period. This is called strong condition. Weak condition, strong condition. These two together, these are called Dirichlets conditions. Dirichlets conditions are significant conditions, important conditions for the existence of meaningful Fourier series expansion for periodic signals. Let us spend some time on understanding the strong condition, Dirichlets strong condition. This strong condition, it involves convergence. It describes convergence of the series. Here, three types of convergences. These are described. Better to have some idea regarding these three types of convergence. Uniformly convergent series. If the series require fixed number terms at every value of time t to converge within an arbitrarily small error, then the series is said to be uniformly convergent. This is highly desirable. Uniformly convergent series is highly desirable. Point-wise convergent series. If the series require different number of terms at different times t to converge within an arbitrary small error, then the series is said to be point-wise convergent series. It is less desirable. Third one is convergence in mean. If the energy of the difference between x of t and corresponding finite term series expansion approximation approaches 0 as the number of terms approaches infinity, then such a series is said to be convergent in mean. Convergence is an important aspect. A few points regarding frequency spectrum. In the beginning of the session, it is mentioned the most important or significance of Fourier series expansion is that it makes visible the frequency content of the signal to us. Just by mere watching at the Fourier series expansion of a signal, one is able to know, one is able to see without any difficulty the frequency content. Of course, once frequency content is known to us, then we can estimate the capacity of the signal to carry information. Frequency spectrum is a term used to denote frequency content of the signal. A few points are given here describing the term frequency spectrum. It is a graphical representation of amplitudes of various frequency components of a signal. So to begin with, one has to understand that it is a graphical representation, a picture. It gives amplitudes of various frequency components. For periodic signal, the spectrum consists of only at fundamental and harmonic frequencies called discrete or line spectrum. For periodic signals, it is a discrete. For non-periodic signals, you are going to see it is continuous. The quotients of exponential Fourier series are complex, having both magnitude and phase, so it requires magnitude as well as a phase spectrum to represent a periodic signal in frequency domain. Magnitude spectrum is even, symmetrical about the vertical axis passing through the origin. Phase spectrum is odd, antisymmetrical about the vertical axis passing through the origin. A few points regarding Gibbs phenomena. Infinite Fourier series exhibits oscillatory behavior at the points of discontinuity. What exactly is this? Let us consider a pulse train, periodic pulse train, and let us consider a single pulse like this, one pulse in the pulse train. Now, Fourier series, this is periodic function and it fulfills Dirichlets conditions. So one can expand this pulse train in infinite Fourier series. This infinite Fourier series, if we plot, then it instead of pulse, exact pulse, it gives a waveform that exhibits oscillatory behavior like this. Here also, it exhibits oscillatory behavior. Here some oscillations. Of course, the amplitude of the oscillations decreases. It is decreasing. This is called Gibbs phenomena. Series exhibiting oscillatory behavior at points of discontinuity is Gibbs phenomena. Some more points are given here. The infinite Fourier series exhibits oscillatory behavior at the points of discontinuity. An overshoot of about 9% of the amount of discontinuity exists. Overshoot. This overshoot is 9% of the discontinuity. Oscillations frequency is equal to number of approximating functions. See, here are oscillations. They have certain frequency. That frequency is equal to approximating functions. Even as n tends to infinity, oscillations and overshoot do not vanish. How large may be the number of functions you are considering? It doesn't matter. Overshoot exists, oscillations also. Some points regarding power spectrum. What is this power spectrum? First, what is power? Usually, signal refers to voltage or current waveform. Sometimes it can be waveform of a field, electric field or magnetic field too. Voltage or signal or field waveform is basically signal. Now, voltage waveform or current waveform, field waveform also, they are associated with a certain power. Voltage is associated with the power V square by R. Current is associated with power I square R. Similarly, electric field associated with power E square by eta. So fields as well as voltages and currents are associated with the power, and hence signals are associated with power. The power of a periodic signal, it is by definition 1 by t integration t f of t whole square dt. Actually, this is a normalized power. Normalized means if you consider voltage waveform, for voltage, power is V square by R. R is resistance. When R is assumed considered as 1, then power becomes V square, simply V square. Similarly, if you consider current, power in the current waveform becomes I square R. If R is considered as 1, power becomes I square. This V square, I square, these are called normalized powers. Here resistance is assumed to be 1. Here the definition, in this definition, P is a normalized power of a signal, periodic signal. So some more points he is giving here regarding power spectrum. The frequency spectrum of f of t represents amplitudes of various frequency components of f of t. There is a power associated with each component. This is an important aspect. Power spectrum refers to a description, a graphical description of the amount of power that is associated with each frequency component of the signal. The signal means several frequency components. Each component has its own amplitude. That's okay. Here the point is each component is also associated with a certain power. Graphical description of that power distribution among various components of the signal, it is power spectrum. It is called power spectrum. The power spectrum of Ft is a representation of power associated with frequency, various frequency components of f of t. It can be shown that P is 1 by t integral t absolute f of t whole square dt. It can be shown, see this is time domain, power definition, and a little bit of manipulation can give us that this defining power relation is equal to sigma minus infinity to plus infinity Fn whole square. Here Fn is exponential Fourier series quotient. There is a theorem, Parrys theorem. This theorem we encounter several places in signals and systems. Let us spend some time on Parrys theorem. Parrys theorem states that the power in a periodic signal is equal to the sum of powers of all its components. When applied to the exponential Fourier series, it becomes P equal to 1 by t integral t f of t whole square dt, which is equal to sigma minus infinity to plus infinity Fn whole square. For periodic signals, if the spectrum of power associated with each frequency component is plotted, can be noticed it is a discrete and symmetrical about the vertical axis passing through the origin. Power density, another term. The power density function, it is indicated by P of omega. Omega stands for angular frequency. Of course, P is a standard symbol for. This function represents the power of a periodic signal per unit bandwidth. Power per unit bandwidth. The total power then becomes 0 to infinity P of omega d omega equal to 1 by t integral t f square t dt. The right hand side represents the mean square value of f of t, and hence area under power density function is equal to mean square value of t. So before concluding, let us recollect the aspects, main aspects which we touched. Frequency content of a signal determines information carrying capacity of the signal. As it is, when the signal is in time domain, its frequency content is not visible. If we want to know, maybe to estimate its information carrying capacity, if frequency content is required, then we have to convert the signal from time domain into a domain called frequency domain where frequency content is visible. Several different techniques are available. It depends upon the type of signal. For continuous time periodic signals, the technique that got developed that is available is infinite Fourier series expansion. The number of terms in the expansion, they are infinity, that's why it is called infinite Fourier series expansion. This is end of the second session. With this, total treatment of infinite Fourier series is completed. Hope you have benefited by listening, by watching this video. We meet again soon with another topic, with a new topic in another session.